We're continuing on with finite differences. That first one was to give you the general idea of it and to talk about calibration. This next one, the pumping well, is mostly because it looks really cool, and also to give you a feel for what a drawdown cone of depression looks like. And then the third one is on a dam flow net, and we go more into the different boundary conditions. So this one with the pumping well, we have four corners with known heads. And so what we're going to do is make constant heads around there. And then we're going to write our nearest neighbors. That's the four around it divided by 4 for each cell. And then we'll calculate that and see what it looks like. And it should look like this. And then we'll start our pump. And we're going to put 50 in one cell. So these are like 190. So we'll put a 50 in there, and then we'll let it draw down, and it'll change as we iterate to the equilibrium condition, but it's just really equilibrium, and then we converge to that. So let me pull over my spreadsheet and show you that. So here's my setup here. I had the four corners, and then I filled in constant head, walking down from 100 to 90, then 90 down to 80. And then this is going to be the one we put in 50 on the second step. But the first time around, I'm going to draw the four nearest neighbors. So it's the one above, plus the one below, plus the one to the right, to the right, to the right, oops, plus the one to the left, over 4. Boom. And then I copy that for the whole domain there. And then I iterate F9, 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 a whole bunch of times. If I look down here, looks like I have a pretty smooth transition across it. So it's basically a flat plane sloping from the upper left corner down to the lower right corner. I changed this one back to yellow so you can see where it is, and I'm going to put a 50 in there, and then I will iterate. I actually set it back to one iteration at a time just so we can kind of see it going with time. So come down here just to look at it, and I hit F9 to iterate. And so it brings that down, and then as we go, that radius of influence, or really the radius, spreads out over time until it comes to equilibrium. I'm hitting F9 a whole bunch of times, but so it eventually comes to equilibrium, and that's what it looks like. So this would look what the real thing would look like, and that process as it spread out, that's what happens over time. This is just a artifact of the iteration. We saw it over time, but that is, once we get to the time-dependent part, that's what it would look like. The third one is the dam flow net. I'll try not to make many dam jokes here, but we got to get all these boundaries here. So what do we do? So the top is easy, right? So if we say the bottom boundary, we set that as at an elevation of 0, and then the water level is at 420 feet, so the top of this 420 cell, then we know the head up there is 420. So it's 420 all up there. And then so we have a top boundary. We're going to put all those cells, we're going to make 420 all along there. Now, what should we do first? Maybe the left side. All right, so the left side, somewhere over here, the water is flowing just that way. And actually, I should have made the point on the last one that how far you put out, the boundaries affect it. So the farther out your boundary is, or the more cells you have, the more realistic it is. So somewhere out here, the water is flowing just sideways. It's not flowing down. It's not flowing down, so the change in head with y, if x is horizontal and y is vertical, the change in h with y would be 0. So if this one is 420, it doesn't change in y, so the next one is 420, and the next one is 420, and so on all the way down. So that functions as a constant head. we said before, and this is from the book, the constant had no gradient or flow parallel to the boundary. So our flow is going from left to right, perpendicular to the boundary. So if the flow is perpendicular to the boundary must be an equipotential line or the same head. So we have the same head all along the side, so it becomes a constant head boundary. The bottom is going to be a no flow boundary, so it's impermeable across the boundary, so we can't have flow going across it, so it becomes a flow line. So down at the bottom here, we have flow only going that way. So it's not going up and down. So it's a no flow boundary. It's 420 along here, but it is changing this direction. This one here is 420, but then it's going down. So out here, it's something less than 420 because it's going down. So I can't just make these all 420. What do I do? Well, this one, the change in head at the bottom boundary over the change in y equals 0, but the change in x does not equal 0. So what we can do on that is if the change in head, change in y equals 0, then I'll go over here. This one here must equal this one here. We don't have one there. That's outside of the domain. So there are a couple ways to do that in our spreadsheet. We can just have a cell down here. Maybe this is C, and this is 4, 5, 6. We just have this one down here equal to C5 or C4 across it. Usually we like to jump over it too. So then we have the nearest neighbors in this one here. And then what that cell sees, it says this one plus this one plus this one plus that one underneath. We call that a fictitious row, and it'll calculate. The other way to do that is we can put in this cell, instead of making a fictitious row, we can just in this bottom row here, we can have this one plus this one plus this one plus, just do that one again. It functions the same way. So there's two different ways to do that. So we do that all along the bottom there. And then we also have no flow boundaries up here. So I do the same thing for this one in the x direction. I put a fictitious cell here, fictitious column, where this equals this one across there, or I write the 4 nearest neighbors for these cells, and I put the one to the left of them twice. And then here I do the same thing, except now it's the top boundary instead of the bottom boundary. So I have this one plus this one plus this one plus this one plus this one again, or again, I make a fictitious one there that equals the one below. Do you follow all that? Then out on the right here, we have a water level here at 220. So we know the head is 220. And so we have 220 all along that boundary. And then again here, somewhere out, and the farther out you put it, or the more cells you have, the more realistic it is. If I put the boundary close in, it squeezes the water a little unnaturally in there. So I have flow going that way. So it works like it did on the left, where we had 420 all the way down. Here we have 220 all the way down. So I think that's all our boundaries. And again, in everything else in the middle, we have the 4 nearest neighbors formula for every cell in here. All right, let's see if I can do this. I have the power of pause and re-record. If I mess up, you'll never know. All right, so on the top here, again, we have 420. Well, wait a minute, this is at 320. No, its elevation is at 320, but it's got 100 feet of water on top of it. So these are all 420. This corner one doesn't make any difference because it's not going to be used for anything, but I'll put a 420 in there too. So all across there, it's going to be 420. And then because, as we said, there's no change in the y direction because the flow is all going from left to right, it's 420 across the bottom there. Then On the bottom, it's going to be, so this is my domain. Here's the line at the bottom at 0. I'm going to put a fictitious row or fictitious node at the bottom here. So I'll make that one equal to 1. I'll do 2 above it. I'm not sure why that works better, but it seems to. And I'll do that all the way across. I understand that goes off your screen a little bit. And then I have a couple more boundaries. So along here, I'm going to do a fictitious one, and I'm going to make this equal to that one across there. So again, my numbers are going to be calculated in here, but I'm putting a fictitious node in there. And then this one here in the corner, do I make it equal to that one, or do I make it equal to that one? I don't know that it makes any difference, actually. It might, but I don't think it does. So this one here, I'm going to make it equal to the 1, 2 down there. And then I'm going to take that across. All right, let me adjust your screen here, move over a bit. So the other boundaries here, these are all going to be 220. Again, the elevation is 200, but it has 20 feet of head on it. 20. And then across to there. And then the same story as on the left side, because there's no change in the y direction. It's going to be all the same up and down. 220. Again, the deeper we go, the more pressure head it has, the less elevation head it has, but it has the same head. For the whole interior here, I'm going to do the 4 nearest neighbors. So equals the 1 to the right, plus the 1 above, plus the 1 below, plus the 1 to the left, over 4, in whatever order. So all the zeros around there, so it thinks it's 0. So I'm going to copy that and paste it there. And then paste it there. I guess the way I set this up, I have to paste it right there too. All right, I think I got it. So now I'm going to recalculate F9. It's got boundaries, and so it might take a while to recalculate. We'll look at it here. Recalculate, 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 recalculate. Yeah, I think we about got it now. Don't you think? And you can probably pretty this up better than I did. So over here on the left somewhere, we have flow only in the x direction. And then along the bottom here, it's going only in the x direction. And then the rest of it, it's going perpendicular to so these color changes, I can make those contour lines if I want. I think the colors look cool, but I can make black and white contour lines if I want. So the flow is going, whoops, that one's not very perpendicular to those. So if I draw my streamlines, it's going to look something like that. Whoops, it's got to head back up there. Again, we have, maybe I should have made this boundary further out so I'm not squeezing it. Perpendicular, perpendicular, perpendicular. So my streamlines look something like that. For the homework assignment, you can just turn that in. You don't have to draw streamlines on it. For the exam, I might make you draw a flownet like this, where you draw the equipotential lines and the streamlines. That was a run through the Laplace equation, which we turned into a finite difference scheme as an introduction to groundwater modeling. Hope that helps.